This is Mr. Martin, and this is video notes for section 8.2 and 8.3. We're going to be talking about similarity and methods to prove triangles similar. So for section 8.2, informally, when we talk about similar figures, we're talking about figures that have the same shape but not necessarily the same size. So you're going to produce similar figures by a dilation, which would be an enlargement, so it's getting bigger, or a reduction. So when you think about similar figures, if you think about if I put on the overhead a picture of a triangle, and then if you remember, if you zoom in or zoom out on the overhead, the triangle would get larger or it would get smaller. So the size would be changing, but the shape wouldn't be changing. That's basically what we're talking about with similar figures. So the definition that we're talking about, if two polygons are similar, the ratio of the measures of the corresponding sides are equal. So if I make ratios out of the sides that match, all of those ratios would be the same, and the corresponding angles are congruent. So be really careful with the definition here. The ratios of the corresponding sides are equal. Okay, this is a ratio. And then the corresponding angles, though, are congruent. And then we have a theorem. If two polygons are similar, then the ratio of the perimeters equals the ratio of any pair of corresponding sides. So let's just take a look at two triangles. I'm going to give this side A, B, and C, and then this would be angle A, angle B, and angle C. And then I'm going to look at another triangle. We'll make this D, E, and F. So capital F up here. So this would be side D, side E, and side F. Let's fix this one up here. This is a capital F. So if I tell you that triangle ABC is similar to triangle DEF, and notice my symbol for similarity, it's just the top of the congruency symbol, the ratio of the corresponding sides would all be equal. So, and I just put in these lowercase letters to make the ratios easier to write. So I could have the ratio of A to D, those are corresponding sides, and then I could have the ratio of B to E, those are corresponding sides, and the last pair of corresponding sides, C to F, those are corresponding sides. And since these triangles are similar, I know that all of these ratios are equal. That's what we're talking about here with point 1 in this definition. Now for this theorem, it says two polygons are similar, then the ratio of the perimeters. So if I look at the perimeter of triangle ABC, that's going to be A plus B plus C. And if I look at the perimeter of triangle DEF, that's going to be D plus E plus F. And if I look at the ratio of these, so the ratio of the perimeter of ABCD to the perimeter of DEF, it's going to be equal to, this is the perimeter and that's the perimeter, but it's also going to be equal to the ratio of any pair of corresponding sides. So it would be equal to A to D, or B to E, or C to F. Okay, so if you know two polygons are similar and you want to find the ratio of the perimeters, you don't necessarily need to know the perimeters, you just need to know a pair of matching sides, a pair of corresponding sides. And we'll look at that in an example later. Alright, so section 8.3, we've done a lot with proving triangles congruent. Now we're going to prove triangles similar. So we have a couple other different methods for proving them similar. We have the angle postulate. So if there exists a corresponding correspondence between the vertices of two triangles such that the three angles of one triangle are congruent to the corresponding angles of another triangle, then the triangles are, let's fix this over here, similar. Make sure you make that correction. Okay, so normally we're not going to use this postulate ever because we know that if by the no choice theorem that if two angles of one triangle are congruent to two angles of the other triangle, that the third angles have to be congruent. So really, angle angle is going to be plenty. So here's our angle angle similarity. So if two angles of one triangle are congruent to the corresponding angles of another triangle, then the triangles are similar. So really, this is our first method for proving triangles similar. We don't really use angle angle angle, but we will use angle angle similarity. So two angles of one congruent to two angles of the other, the triangles are similar. Now we have another method here. If the ratios of the measures of the corresponding sides of two triangles are congruent, then the triangles are similar. This is side, side, side similarity. So when I talk about the ratios, we're talking about fractions made out of the length. So let's say this is 3, and this is 4, and this is 5. And then I have another triangle over here, and this is 6, and this is 8, and this is 10. So we've got ABC, and I've got DEF. So since the ratio of AB to DE is equal to the ratio of BC to EF, which is equal to the ratio of AC to DF, so all these ratios are the same. They're all happen to be 1 to 2. The triangles are similar by side, side, side similarity. Okay? So that's our second method, side, side, side similarity. So you need to get the ratios of all three sides, make sure that they're the same. And then our third method here is side angle side similarity. So the S's here stand for ratios of sides, and the angle is for congruent angles. So if the ratio of the measures of two pair of corresponding sides are equal and the included angles are congruent, so we've got the ratio of the corresponding sides equal, and we've got the included angles are congruent, then the triangles are similar. So again, just a quick example here. A, B, C. Let's say this is 5, and this is 6, and this is 30 degrees. And here's triangle DEF. And let's say this is 10, and this is 30, and this is 12. Since AB to DE is equal to BC to EF, and they're both 1 to 2, so 5 to 10 is 1 to 2, and 6 to 12 is 1 to 2. And angle B is congruent to angle E. The triangles are similar by side angle side similarity. So those are our three methods. Let's take a look at a couple of examples. Given that polygon ABCDE is similar to GHIJK, we want to find the length of the missing sides. So what we're looking for is a pair of sides that correspond and that we know the measures of both of them. So I can find the ratio of the polygons, and I know that the ratio of all the other sides has to be the same. So I know that the ratio of all the sides has to be 3 to 4.5, and if I want to get rid of the fractions, I can just double those, so that would be 6 to 9. And then I could reduce that again, divide by 3, so that would be 2 to 3. So this is my basic ratio of the polygons, is 2 to 3. So I know the ratio of all the other sides has to be 2 to 3. I could have also gotten it from this pair of sides. So now what I want to do is I want to find IH, JK, and GK. So I know that 2 to 3 is going to be, so let's find IH first. So the corresponding side on the smaller polygon is 2.5 over segment HI, and then we can go ahead and solve that. So we're going to cross multiply. So I have 2HI is equal to 5, and HI is equal to 2.5. Let's see what I do. That should be times 3. So that should be 7.5. So that's 3.75. So this side here is 3.75. And then let's find JK. So again, I know the ratio of all the sides is 2 to 3. So that's going to be 2.75 over JK. So I know 2JK is equal to 8.25, which means that JK is going to be 4.125. So this is 4.125. And then I need the last side here. So again, 2 to 3 is the ratio of the polygons, and the corresponding side on the left is 2, and that corresponds to GK. So I have 2GK is equal to 6, which means that GK is equal to 3. So this side is 3. So part B, I want to find the ratio of the perimeters. Now we could add up the sides of polygon ABCDE and do the same thing with GHIJK and then find the ratio of those. But since these polygons are similar, I have a theorem up here, this theorem, that says if the two polygons are similar, the ratio of their perimeters is equal to the ratio of any pair of corresponding sides. So really, I have the answer already. The ratio of the perimeters is going to be the same as the ratio of the corresponding sides, 2 to 3. Alright, so I'm going to end this video here, and then we'll have another video to complete the examples from section 8.3. If you had any questions, make sure you write them down in the margins and ask me next time you see me in class, and we'll see you next time.